So the second speaker is Federico Ghimenti from the Stanford Institute of Theoretical Physics. Federico got a master in theoretical physics in 2021 at École Normale Supérieure in Paris, working with Giulio Biroli on phase behavior of two-dimensional solids under shear flow. Then a PhD at the University of Paris-Cité with Frédéric Van Wieland on irreversible sampling of glassy dynamics. And so since then, he has a fellowship at the Stanford Institute of Theoretical Physics on machine learning and analog computing. And now he's going to give a talk entitled Sampling in Glassy Systems Through Non-Reversible Dynamics. Okay,
thank you.
please, Federico.
Yes, I will share my screen. Okay, and okay, hopefully you can see my screen and my pointer.
Yeah,
And
okay.
okay, that's great. I'm very happy to be here and be able to talk about a big part of my PhD work about how to alleviate a somewhat hard problem that appears in statistical mechanics. So what is this hard problem that I tried to address? Well, in statistical mechanics, the main goal is starting from the microscopic details of interactions and the fluctuations that occur in a system, derive the macroscopic behavior, the collective behaviors and the properties of the system. And in order to do so, statistical physicists exploit the fact that we can treat statistically a huge number of degrees of freedom. And for instance, one of the cornerstone of statistical mechanics is the fact that if I take a system of interacting particles, classical interacting particles that are allowed to exchange heat with an external environment at temperature T, and I ask what is the probability that the system has a certain microscopic configuration C with an associated energy E of C, then this probability assumes a well-known form, the Boltzmann distribution. It's proportional to the exponential of minus the energy divided by thermal energy. And macroscopic observables O can be computed by summing over all the microscopic configuration, weighting by means of the Boltzmann distribution. In line of principle, so deriving the properties of macroscopic system from microscopic interaction is something that can be done, but in practice, the analytical computation of this thermal average is very hard analytically for realistic systems. And so people have resorted in the past 60 years to numerical simulation in order to sample the Boltzmann distribution and transform the pseudo-random number that are generated in a computer into random configuration of your physical system distributed according to Boltzmann. And the way this is done, starting from the seminal work of Metropolis, Rosenblatt, and Teller, is to simulate a stochastic dynamics of the system, where the system evolves and we can track the evolution from one configuration to another, and to choose a specific rule for this stochastic evolution such that in the long time limit, the running averages of any macroscopic observable O of Ci converge to the thermal averages. The problem with this approach for some system of interest is that I need to be able to forget the initial condition from which my simulation was initialized, and I need to be able to reach a stationary regimes. And there are some cases where this happens only after a very long time because of slow convergence that pertains to the physics of the system itself. Now, this is a kind of challenge that appears in fields that go also well beyond the realm of physics. It appears, for instance, in protein folding, where the space of configuration that one wants to explore is the space of all possible protein structure that can be taken by a set of amino acids at a given temperature. Each of these are associated with a certain energy of C, and this energy forms a very rugged landscape as a function of the configuration space that is pictorially represented here. And only a few configurations are biologically relevant, and they're usually separated by very large energy barriers. And typically, the dynamics that are used to simulate these systems get stuck by the presence of these energy barriers. Another related field where this problem appears is the field of machine learning and optimization, where here the space of configuration is the set of weights that of a neural network, and the analog of the energy is the training error that the network is doing when performing a given task. Now, during training, we would like to find the few configurations that have a low error, and usually these systems are very large. They contain a huge number of parameters, and so training them can be very costly, and we would like to do that as fast as possible. But actually, in condensed matter physics, there is a whole class of systems too that fail to sample the Boltzmann distribution and to equilibrate. And these are given by amorphous material and glasses, which here I will use as an umbrella term that encompasses metallic glasses, colloidal systems, foams, that all share the property that they are disordered, very much like liquids, but do not flow or flow extremely slowly, very much like crystal. And the fact that they do not flow is historically represented by these kinds of angel plots, where for a set of glassy liquids, I'm representing on the x-axis the inverse temperature, renormalized by a certain scale, adimensionalized by a certain scale, the glass transition temperature, and on the y-axis, the logarithm of the viscosity. And what you can see is that upon a mild variation in temperature, we have huge jumps in the viscosity. The viscosity can increase by 10 orders of magnitude upon mild variation in temperature. So this behavior is extremely puzzling. How does this dynamical slowing down take place when there is little evident change into the structural properties of the system? And we still lack a fundamental and complete understanding of the slowdown. And in order to sharpen our understanding, numerical simulation are actually instrumental because they allow to resolve the motion of the system at the particle level. And if we look at that, the picture that emerges is that in liquids, typically particles move and diffuse a lot, moving around the system, while in gases, particles are stuck by the cage formed by their local neighborhood, from which they can escape only by means of very complicated rearrangement events. And one of the main goal in the field of computer simulation of glassy physics is to be able to study this event and study the relaxation of this system. But in order to do that, we need many samples of equilibrated glassy systems at a low temperatures. And so the question is, how can we fight the slowdown of glasses and prepare equilibrated glasses at low temperature using numerical simulations? Well, since we are using simulations, we get to choose the rule to some extent. And so what people usually do is resorting to unphysical moves that speed up the convergence to the Boltzmann distribution in numerical simulations. And a paradigmatic way to do that is by constructing these unphysical moves in such a way that they respect asymmetry, a form of reversibility property that I will comment more later on, reversible dynamics that obey detail balance. And there is a whole zoology of moves that can be designed in this way. Cluster moves where you take, when you make collective displacement of the system, parallel tempering when you create many copies of the system at different temperatures and then you exchange them, swap algorithms where you take two particles of different species and you try to swap them, machine learning approach where you try to learn the best move. You have plenty of choices and they all rely on the fact that these moves are reversible. But there is also another another approach that emerged from the field of applied mathematics in the late 90s, and it relies in trying to thinking out of this equilibrium or reversibility box and to use out of equilibrium dynamics that nevertheless sample the Boltzmann distribution. And I will illustrate one of these dynamics later, but here, like what I want to stress is that from the field of applied mathematics, it is known that the reward that you get if you manage to design one of these out of equilibrium dynamics is a faster convergence to the Boltzmann distribution. And this idea has permeated in the realm of physics with application in the study of two-dimensional melting in the past, I would say, 15 years. However, these ideas of irreversible sampling have not been explored very much in glasses and in systems where there is a form of glassy slowdown. And this is the gap that my thesis aimed at addressing. So I will illustrate a minimal implementation of this irreversible drive, and I will ask how effective it is in systems like supercooled liquids of glasses, where in regions especially where the relaxation is low. But first, let's give a more precise meaning to this notion of equilibrium sampling that I mentioned in the introduction. So here, the task is I'm given d-dimensional degrees of freedom with an energy V, and I want to sample the Boltzmann distribution for these d-dimensional degrees of freedom. And so the way to go in equilibrium is to endow the degree of freedom with an overdamped Langevin dynamics that is made up by two terms. One term is a gradient descent that helps exploration convergence toward local minima, and another term that is a white Gaussian noise at temperature T, which kicks the particle around and allows exploration of the configuration space. Now, this is a stochastic equation of motion, so it has a probability distribution associated to that, and we can study how it evolves. It evolves according to a continuity equation with a current J, and this current J contains two terms that correspond respectively to the drift and the diffusion term that appeared in the overdamped Langevin dynamics. Now, what is the stationary solution of this partial differential equation? It is the Boltzmann distribution, in the sense that the Boltzmann distribution makes the current in the Fokker-Planck equation divergenceless. But also, the Boltzmann distribution in this case is an equilibrium solution. The current evaluated at the Boltzmann distribution becomes exactly zero. And so there are no net currents in the system in its stationary state, and that's the equilibrium property and is associated with a zero net entropy production rate. Now, we can also study, since this equation is linear in rho, we can also study the non-stationary solution, and we can write that the probability distribution at time t is equal to the Boltzmann distribution plus some error that decays in time exponentially, and the time scale over which this decay happens is the relaxation time, defines the relaxation time of the system. And so the goal is to reduce the relaxation time as much as possible, because that's the time one typically needs to wait in order to obtain an equilibrated system using these dynamics. How to do that? Well, we saw here that rho B is the stationary solution, and then it's also equilibrium. So somehow we would like to avoid having zero current. We would like to enforce some current in the system and somehow drive it toward the Boltzmann distribution. So what we're going to do is to add a force F of R to our overdamped Langevin equation, which will add also a current in the corresponding Fokker-Planck equation, of course. And then we are going to impose that the Boltzmann distribution is the stationary solution of this Fokker-Planck equation. This means imposing that the divergence of this term, of the extra term coming from the external drive, is zero when evaluated in the Boltzmann distribution, and it gives this condition here, shown here. But we can have that the extra current that we are adding is actually different from zero in the steady state. So the divergence is zero, but the extra current is different from zero, and this is a signature of an irreversible dynamics. And actually, there is a mathematical theorem that that was proved at the beginning of the 90s that tell us that the relaxation time of the system in the presence of this extra force that satisfies this condition of stationarity of the Boltzmann distribution is always smaller or equal than the relaxation time of the corresponding equilibrium dynamics. So this is really telling us that if we find an F with this property, we are going faster. But there are two questions then. One is, what is a practical implementation for this F? And I chose a minimal implementation for the F, which are the transverse forces. And these are obtained by multiplying the gradient of the potential by an antisymmetric matrix A, so that this condition here is satisfied. The extra current is divergence-less. And the other question is that, okay, this is a mathematical inequality, but how much actually do we go faster, and how does the speed up depend on the temperature and the details of the interaction of the system? So in order to answer this question, I turn to the study of how transverse forces operate in dense liquids. So what I will be interested in is n particles in d dimension that obey the following overdamped Langevin equation of motion, where the force F is made up by two contributions. One is the gradient of a central force, and the other term are transverse forces, and they are represented schematically here. So in blue, there is the gradient of the central force, and in red, there is the transverse forces. And already from this picture, we can kind of get an intuition that when two particles will collide, the transverse forces will allow the two particles to slide one across each other, and will increase the diffusion, the diffusivity of the system. And I will encode the strength of the driving into a parameter gamma that sets how strong are the transverse forces inside the system. So I want to understand and quantify the speed up, and this will be done in practice by means of numerical simulation and in theory through two analytical approaches, and I will tell you the results of one of these analytical approaches. But let's start with the numerical simulation. We simulated a Cobb-Anderson mixture. It's a binary mixture of classical particles of two species. So there are big particles and small particles that interact by means of a truncated and shifted power law potential. And I need also a choice for A, and here I'm in 3D, and I took transverse forces to act within the XY plane. And it turns out that this choice is quite general up to a rescale of gamma and a overall rotation of the system. So what are we up against? What happens first when transverse forces are not turned on? Of course, there is a I won't condense all the phenomenology of glassy dynamics in this presentation. Here I will focus on one of the observable that we use to quantify the speed up, and this observable will be how much particles move in real space. And one way by which this can be done is by measuring the mean square displacement of the particle, which at long times enter a form of diffusive behavior. And this is a plot for the Cobb-Anderson mixture at equilibrium, so without transverse forces, as the temperature is changed. And what we can see is that at high temperature, particles quickly enter a diffusive regime, while at low temperature, there is a long-lived plateau that is a signature of that caging phenomenon that was sketched in the introduction. Now, how does this mean square displacement change? And one other thing that I would like to add is that if we look at the structural properties of the system in a naive way by looking at the Fourier transform of density-density correlation function, we can see that we have a mild variation in temperature, and we have a huge change in the relaxation time, or the typical time it takes to the particle to diffuse by an amount that is comparable to their diameter. And we can see that the structure factor only mildly changes from the liquid to the glass, where the relaxation is very slow. And this is one of the signature of small changes in the structural properties of glassy system. So now that we have a glance of what happens in equilibrium, let's look at what happens when we are out of equilibrium and there are transverse forces injected into the system. So the first thing that I want to check is that I am sampling Boltzmann, and I'm doing that faster. And this is shown first in the figure here on the left, where I'm plotting the structure factor of the system for equilibrium dynamics, and these are the colored line at two different temperatures, and then in the presence of transverse forces, and these are the dashed and the dot line. And we can see that the curves match, which means that even in the presence of transverse forces, I replicate the structure of the system. So this is a signature of the fact that I'm sampling the Boltzmann distribution. And on the right, I'm showing a plot of the mean square displacement of the system at a temperature where diffusion is mildly slow for different values of the driving gamma. And what we can see is that as I increase the strength of the driving of transverse forces, the particle diffuse more and more, and the mean square displacement becomes larger and larger at the same fixed time. So particles are moving faster inside the system in the presence of transverse forces. But what is the overall speed up of the system as the temperature is changed? Well, what I can do is measuring the long time limit of the mean square displacement obtained at the diffusion constant, and then plotting the ratio of the diffusion constant with transverse forces against the diffusion constant at equilibrium. And this will be a measure of the efficiency of transverse forces. And I plot this quantity as a function of the inverse temperature. So what we have is that at high temperature, thermal fluctuations mirror out the effect of transverse forces. And then as I lower the temperature, I obtain an interesting non-monotonic behavior with a peak in the efficiency provided by transverse forces at moderately high temperature, which then decrease. And as I enter into this right panel here, which contains the slow part, the temperature at which relaxation is low, we have that the efficiency degrades more and more. And so can we rationalize this? Because at the end, in the slow phase, the transverse forces look very much like equilibrium, but they are not equilibrium because they drive the system out of equilibrium. So where does this non-equilibrium drift operates then? And in order to answer this question, we can look at other form of transport in the system. We can look at the full diffusion tensor of the system. And this full diffusion tensor is usually for equilibrium dynamics is a symmetric object because of Onsager reciprocity relationship. But when I'm out of equilibrium, this object can acquire an antisymmetric contribution that has recently been widely investigated also in chiral and active matter systems. And what this antisymmetric contribution to the diffusion tensor measure, what this odd diffusivity represented here measure, it's a form of swirling motion of the particle. For instance, for transverse forces, here I'm showing short time trajectories for equilibrium dynamics and in presence of transverse forces. And you can see that for equilibrium dynamics, there is little wiggling and jiggling of the particles. And in the presence of transverse forces, there is a form of chirality, chiral motion enforced in the XY plane from transverse forces. So I can measure this odd diffusion constant and I can add it to the map of the speed up that I was showing before. And so what
I have 5 minutes.
Thank you, yes. And so what we're showing here is a plot of the efficiency of the system as a function, again, of the inverse temperature. But here I'm adding these purple and magenta symbols, which are measurements of the odd diffusivity of the system. And what we can see is that at large temperature, odd diffusivity is almost 0, and then its modulus increases. In particular, it increases steeply in correspondence to the peak of efficiency, and then it goes to a plateau, and it stays constant in the region of slow relaxation. And the picture that this measurement conveys is that at low temperature, the particle in the supercooled liquid swirl without relaxing, and that the dynamical pathways unlocked by transverse forces collapse in the glassy phase into closed loops and closed orbits. So these are the results from numerical simulation. Can we rationalize that from theoretical approaches? Now, in glassy systems, we have very few microscopic, we still don't have a full microscopic complete theory of the glass transition, but we have approximated theories. And one of them is a dynamical mean field theory, which is essentially a mean field approach, but to study the dynamics of the system, and is obtained by embedding the particles in an infinite dimensional space. I will not give you more details about this approach. What I will tell you is that with within this approximation, this mean field approximation, we can derive expression for the diffusion constant and the odd diffusivity as a function of this m hat, which is a low frequency mode of force-force autocorrelations of the system. And what the outcome of the theory is that at low temperature, there is an ergodicity breaking transition where the system gets stuck. And this temperature is the same for transverse forces and for equilibrium dynamics. And as I approach the dynamical transition temperature, the diffusion constant tends to 0, but the odd diffusion goes to a non-zero constant. And then we can study the system at low density and produce curves that qualitatively match the ones that were found by means of numerical simulation. So you see, we have for the efficiency, we have a peak and then a degradation of the efficiency. And for the odd diffusivity, we have a steep increase in the diffusion constant. And we can obtain similar results also by using finite dimensional approximation schemes, such as the mode coupling approximation. So I'm heading toward another thing is that we can compute many more transport coefficients like the mobility and the viscosity, and they all convey the picture of a dynamically arrested swirling liquid. So I'm heading toward the conclusion. What did we learn is that approaching the glass, the efficiency degrades because of this collapse of the dynamical pathways into closed loops. And where to go from here? Well, one can ask if we can drive other degrees of freedom, and this is the second part of the story of my PhD about how to drive, for instance, the diameters of the particles out of equilibrium. Another question is, what is the optimal non-equilibrium drive? Because I started just from a minimal implementation, but what is the best force that I can apply? And what are the applications beyond glasses, like in systems, in quantum mechanical systems or in neural network? And thanks a lot for your attention.
Thank you. Thank you very much, Federico. Question or comment?
I have a very, hello, can you hear me?
Yes.
Yeah, yeah.
So, very naive question. So maybe just because I'm out of the field, but so in the end, you wanted to explore better somehow the region around the possible minima, and your strategy was to change the deterministic part in this stochastic equation.
Yes.
Would it make sense and could be a part that could be explored to act on the noise? So looking for example, for noise term that has longer range correlation, that so in a say would explore not only the neighborhood but far away from that. So.
That's yes, that's a very good question. Yes, it is possible. You can add a generic diffusivity matrix, and then there is the interesting question: you can make the noise space dependent, or you could add some form of some form of memory. So if you add memory, is actually very similar to transverse forces. But if you add instead a space dependency to the noise, you can do more interesting things. And this is something that we have explored a bit during the PhD. And the effect is rather different with respect to the transverse forces one.
Okay, thanks.
Other questions or comments? Actually, I have one. Mm-hmm. If I have well understood, I mean, your goal is to have a fast sampling, I mean, but to obtain an equilibrium measure.
Yes.
So, but if you consider a non-equilibrium sampling, that is to say sampling that breaks the detail balance, I mean, what are the rigorous results telling you that actually you measure an equilibrium, finally you sample an equilibrium measure?
It's really the stationary condition from the master equation, let's say. Like detail balance, it's
okay, because the equilibrium solution is also the stationary solution. Okay.
Exactly.
Okay.
Exactly. Okay. Yes. And this is fully rigorous, I would say.
Okay. Thank you. Okay. Thanks. If there are no other question, okay, I would like to thank both speakers, Alessandra Colla and Federico Ghimenti, and
thank you.
See you again on this screen next month. Okay. Bye.
Thanks a lot.
Ciao.
Ciao. Thank you very much. Grazie dell'organizzazione.
Ciao.
Ciao.